The next topic in 7.1 was called coterminal angles. Coterminal angles. So let me open the textbook here, and I'll try to write in the book itself so that you can see what the problems are. So first, what do we mean by coterminal angles? So if you, let's say that you have an angle of, say, 60 degrees, positive 60. And then if you keep going in the counterclockwise direction and go one full circle and come back to the same terminal side, so basically you have added one full circle or 360 degrees to this angle of 60. So now you have 360 plus 60, which is 420 degrees. So basically, as you can see, both the 60-degree angle and the 420-degree angle, they both have the same terminal side. Any set of angles that have the same terminal side are called coterminal angles. So as it, it should be obvious that you can keep adding as many 360s as you want, and you'll keep coming back to the same terminal side. Similarly, if you go clockwise, say from here, then each time you complete one circle, you're subtracting a 360 because clockwise angles are negative. So by either adding multiples of 360 or subtracting multiples of 360, you can get a whole set of coterminal angles. Similarly, if you're working in radians, then 2 pi radians, multiples of 2 pi. If you add multiples of 2 pi, you get a set of coterminal angles also if you subtract multiples of 2 pi. So let's look at problem number 50 over here. The problem says, for the following exercises, find the angle between 0 and 360 degrees that is coterminal to the given angles. Now this is a negative angle, so to get an angle between 0 and 360, which is coterminal with this, you'll have to add 360 to it. So negative 40 plus 360. And that comes to 320. And as you can see, it's an angle between 0 and 360, and it is coterminal with negative 40. Let's look at problem number 53. Now, starting with this huge angle, to get something between 0 and 360, you will have to subtract 360 many times before you get to that 0 to 360 range. So in fact, you'll have to subtract 363 times. And you can do this on your calculator. Just start with 1400 and subtract 360, subtract 360 again. Keep doing it until you get an angle between 0 and 360. And this actually comes out to 320 degrees. So that's the answer for number 53. Let's now look at an angle in radians. So say number 55 over here, 10 pi over 3. And here we have to find an angle between 0 and 2 pi, which is coterminal with this. 10 pi over 3 is bigger than 2 pi, because 2 pi would have been 6 pi over 3. So you'll have to subtract a 2 pi to get the correct answer. So minus 2 pi. And then we use a common denominator of 3. So 10 pi over 3 minus 6 pi over 3. And then keeping the same denominator, you subtract the numerators. So 3, 10 minus 6 is 4. So your answer is 4 pi over 3. The next topic in this section is what's called, it has to do with rotational motion. So there are, I'm going to give a little bit of basics and then do a few problems. Now, when we talk about speed, how fast something is moving, the idea we have in mind is that some distance divided by some time, and that is called linear speed. It's the speed when something is going along a straight line. So this equation here is the equation for linear speed. Linear speed. Linear speed is equal to distance that you cover divided by the time that you take to cover that distance. Now, instead of going along a straight line, if something is moving along a circle, so for example, let's say that this is a disk which is rotating around the center. And then if you consider a point at the edge of the disk and follow it as, say, the disk is rotating counterclockwise. So at a certain point in time, the disk is over here. And let's say that at a later time, that point has moved to there. So during that time, the radius has gone through a rotation equal to that angle. So if I call that angle theta, and if this bit of rotation has taken place in a time t, then we define angular velocity using this equation. So instead of distance over time, angular velocity or angular speed is angle of rotation over time. The symbol that we use for linear speed is v, and the symbol that we use for angular speed is this letter, which looks like a W, but it's actually the Greek letter omega, lowercase omega. Now, we know how S, a linear distance, and theta are connected with each other. Now, even though this point is moving along, it's rotating, you can also think of it as it's a linear motion. That point has covered a distance equal to this arc length, S. So you can think of the linear velocity, linear speed of that point to be S over T, and the angular speed to be theta over T. Now we know how S and theta are related. The equation we saw earlier is S equals R theta, where R is the radius. So this here is the radius, which basically means you can write V. If I replace S by R theta, this becomes R theta over T. And here, if you isolate theta over T, that part is equal to the angular speed omega. So essentially what we are saying is V equals R, this R here, times omega. So this is how linear and angular speed are related to each other. And just to give you an example, like if you have a bicycle, if this is the wheel of the bicycle, so as the wheel turns, there are two types of motion going on. One is the rotational motion of the wheels, but at the same time, the bike is also moving in the forward direction. So there's a rotational motion of the wheel, but the wheels are also moving forward. And the rotational, the angular speed and the linear speed of the bicycle are related by this equation, V equals R omega. Let's look at problem number 60. So the problem reads, a wheel of radius 8 inches is rotating 15 degrees per second. What is the linear speed, the angular speed in RPM, and the angular speed in radians per second? Now, just as in using, when we use this equation, S equals R theta, we're supposed to use theta, we are supposed to measure theta in radians, not in degrees. The same thing is true for the equation V equals R omega. The angular speed has, the units for angular speed should be radians per second, not degrees per second. So before we can use this equation to find the linear speed V, because we already know that R is 8 inches and the angular velocity omega is 15 degrees per second. But we can't use this in our equation. It has to be in radians. So first I'm going to convert it to radians per second. Degrees to radians, you multiply by pi over 180. And this can simplify to so 15 times 1 is 15, and then 2. So pi over 12 radians per second. So 15 degrees per second is the same as pi over 12 radians per second. And in doing that, actually, we have already answered the third part of the question, which asked for the angular speed in radians per second. So that answer is pi over 12. And now we can use this omega in this equation to figure out V. So V equals R, the radius, which is 8, and then omega, which is pi over 12. So 8 pi over 12. And you can use your calculator to see that this is 2.094 inches per second. Since the radius is in inches, this would be in inches per second. So that's the linear speed V. And then the remaining part of the problem is to find the angular speed in RPM. Now we already know the angular speed in radians per second, pi over 12. So we just have to convert it to RPM. RPM stands for revolutions per minute. So the way you would convert it is omega equals pi over 12 radians per second. Now we have to convert radians into revolutions and seconds into minutes. So the conversion factor, for the first conversion factor, I want to get rid of the radians and replace it by revolutions. So that radians needs to be in the denominator because this one is the numerator. And if this is in the denominator, we can cancel them. And then I want to replace it with revolutions so that revolutions will be upstairs. Now the relationship between revolution and radian is that one revolution corresponds to 2 pi radians. So that will take care of converting radians into revolutions. And then we have to convert seconds into minutes. Now the seconds here is in the denominator. So in the conversion factor, I want it in the numerator so that they can cancel. And then minutes in the denominator. Now we know that 1 minute corresponds to 60 seconds. And then you just do some algebra. Radians here cancels radians here. Seconds cancel seconds. So as far as the units are concerned, we end up with revolutions per minute. And then the numerical value would be pi times 60 over 12 times 2 pi. The pi's cancel out. And 12 times 5 is 60. So you're left with 5 halves or 2.5 RPM, 2.5 revolutions per minute. So that is the end of 7.1.